Welcome to homework.
Hello everyone, today we're doing chapter 14, problem 64, and this problem tells us that we have this aldehyde called D reacting with this amino alcohol called E in the presence of sodium hydride to give compound F with this chemical formula here. It asks us to determine the proposed structure of F, and it tells us that we have an IR absorption at 1730, so we know that the IR absorption at 1730 corresponds to a C double bond O. And it says that in our carbon 13 NMR, we have 8 lines. And then also gives us the values for a few proton NMRs. So how do we go about determining the structure of F? Well, we know that we have to have an electrophile and a nucleophile, and we're treating with reagents, which is sodium hydride in this case. Sodium hydride dissociates to sodium ions, which is a counter ion, doesn't really do anything, and hydride ions, or hydride anions more specifically. And hydrogen, obviously, it's not happy being negatively charged. It likes to be neutral. So the one way you can do that is to pick up another proton off a portion of this molecule to make hydrogen gas, H2 gas. And the proton it's going to pick up is the most acidic proton. So we can actually determine that this alcohol proton here is the most acidic. So we know that we're going to form an O-, which is going to act as our electron-rich nucleophile. And this nucleophile can go through something what we call nucleophilic aromatic substitution, which we'll learn later, I believe, in chapter 18. But what we know is that with nucleophilic aromatic substitution, we get some sort of addition when we have a leaving group, ortho or metas, to an electron withdrawing group, such as this aldehyde. So what's going to happen is we're going to attack this position, making a bond. We make a bond, you break a bond, so this double bond will break to form here. But when you make a new bond, you need to break a bond, so this double bond will break to form here. When you make a bond, you need to break a bond, so this carbonyl bond will break, go up to the oxygen. But then this is an intermediate, so then at the same time, those 2 electrons that went up to the oxygen nucleus will go back down to reform that carbonyl double bond, making a bond. When you make a bond, now this blue bond will break to go over here, making a new bond. You make a bond, you break a bond, so this black bond will break to make a new bond here. And when you make a bond, you break a bond, so our leaving group, being one of the halides, this fluorine ion, will leave. And we know that fluorine is also not in the final chemical formula, so that we know that this is what's happening with fluorine leaving. And this yields us a proposed structure that looks something like this. And now we can confirm that yes, we have that 1730 aldehyde IR peak in this molecule. We have the correct formulation, and we have the question stem says we should get 8 peaks. So let's count all the unique carbons. We have 1, 2, then let me do this in different colors. We have 1 here, 1 here, and these 2 will be the same. And these 2 will be the same. We have another one here, 1 type here, 1 type here, and then these 2 at the end will be the same because of the free rotation in the sigma bond. So in essence, we have 1, 2, 3, 4, 5, 6, 7, 8. So we have 8 lines in our carbon NMR spectra. And for the proton NMR, well, what should we expect? Well, this proton is kind of coupled to or is bounded to a carbon that has no neighboring proton. So this is supposed to be a singlet. And now these 6 protons are also bounded to a nitrogen, and we know nitrogen and oxygens are not involved in splitting, so we know that these 6 protons will also be a singlet. Now these 2 protons each are neighboring 2 other protons, so both of these should be a triplet and a triplet. And then these 2 protons here are neighboring 1 other proton, so these should be doublets, both of these. So let's see what we have on the NMR spectra. So we have a singlet corresponding to 6 hydrogens at 2.2, which can be this. Then we have a triplet corresponding to 2 hydrogens at 3.05, and another triplet corresponding to 2 hydrogens that corresponds to 4.20, so that can be these two triplets here. And then we have two doublets, one at 6.79 and one at 7.89, and these correspond to two protons each, so they can be those two. And not only that, we know that aromatics have chemical shift values around 7 to 8 ppm, so we have one just under 7, 6.97, and one within that range, 7.82, so we know that these are those two protons. Then we have something that's very d-shielded, very downfield shifted at 9.97, corresponding to a single proton, and it's a singlet. So we know that the chemical formula here matches the IR's data, the carbon 13 NMR data, the proton NMR data, and a molecular formula to propose a structure something that looks something like this.